they have an ordered list of numbers and some number k. We need to find two numbers x and y, such as x and y, x plus y equals to k. For example, if they have this list and number k equal to 9, they have two numbers in this list, 1 and 8, and their sum give to us 9. So this is our result, our solution. How can this solve such a problem? And I will start from the idea how I want to solve this problem. So we can start. The main idea is to do some iterations, and these iterations they can remove the numbers which part of numbers which can satisfy to our solution. So we start from this first number. This will be one of the candidates, so we want to find two numbers, and that's why we need to have the two candidates, two numbers. What if we take as the first candidate this number -2? Okay, if I take as a candidate 1 number -2, what I need to find? Of course, I need to find the number which gives me in the sum this number 9. So this number will be 11. Okay, because -2 plus 11 gives to me 9. Okay, and I fix this number, and I have this subarray in which I want to find 11. And because our list is sorted, we can use a binary search to find this number. Of course, we cannot find it, but if we find this number, then we solve our task. We find two numbers, and we do this with logarithmic time. Okay, but what if I not find this number? If I not find these numbers, I can split this subarray into two groups. The first subarray with the numbers which is less than 11, and the second subarray is the numbers which are greater than 11. And at this point I can say that all the numbers which are greater than 11 can't be in our solution. You can think about this, and this is correct statement, because here in this example we have two numbers. Actually, this is a subarray started from 12 and go into the end of the list, and any of these two numbers can't be in our solution because we chose the minimal number in the whole array, and we need to add 11 to it to give our result. But if we summarize this number -2, all the numbers which are greater than 11, that it is impossible that they give to us our sum, because the total sum will be greater than 9, because all numbers are increasing after 11. So we can remove this subpart with 20 and 30. Okay. And what we do next? At the next step, we looking at the numbers which are lower than less than 11, and from these numbers we can find the second candidate. Okay, so we can say that we can't, at this point we can say that we can't use these numbers 20 and 30, and we can't use -2. Okay, and how we chose the second candidate as C1. as C1 will be the maximum number from the numbers which are less than 11. So we have this subarray minus 1, 1, 4, 7, and 8, and the maximum number from where from here is 8. And we can go to the next iteration where we choose the new C1, which is equal to 8. And now I need to find the C2. Of course, the C2 must be equal to 1 because we need to find in sum 9, and we need to add 1 to 8. And we find this in this subarray, okay? Because we chose this, we remove from our solution space this subarray, and this also this number, and we have only solution space here. And of course we use a binary search to find this number. So in this case I will find it, it will be 1, I will be find it the binary search. But what if I not find it? If I not find it, that's mean that if I not find it, that's mean that I can remove all the elements. So I also split all this subarray into two parts: the less element which are less and the elements which are greater, and I can remove all the part with the less elements because they will not give to me the sum, because these elements will decrease my sum. And of course the next candidate will be the number, the first, the minimum number from the numbers which are greater than our element which we can find, we not find in the list. But in this case we find it and it's okay, and we can say that we find our solution. Our solution is 8 and 1. Okay, so we have here the algorithm that somehow has two pointers from left and the right, and they goes the big steps removing the unnecessary numbers, and they go to the each to other on every step. With a binary search we will find our candidates. Okay, this was the main idea, and now I will implement this in code, and I think things gets more clearer, more clean. Okay. So let's write the type signature for our function. I will call this function find. It takes some list of a's. Of course, a's have some order, and I have some number k. Of course, it is of the same type as our list, and they need to find two numbers. So this means that they need to find the pair of a and a, and of course we can be in this case. Then we have in this one numbers, and we need to use the maybe type here to catch this case. And let's go to the implementation. Okay. What we have? We have some list here, and we have so we can unpattern match. No, we will use helper. So we have some list. We have some element k, and this is our function arguments. So How we will define solution? Of course, as I said, we have an iteration process, and this iteration process can be in two cases, when they go from the right and then they go from the left. Okay, and for each of these cases I will define their helper functions. The first helper function is go, and it's go from the right. Okay, they move from the we want to remove the candidates from the right. And this function, of course, take our it go as a start, as an initial function, and it takes our initial list. And I don't need to provide this key because we have the namespace here, which will be visible to our subfunctions. And of course, I need to define this function. Okay. How we do the definitions of this function? Our function go from the right. It's take this list and it's take the C1, the first candidate, and it has the tail of the list. So we can better match it here. And here we can go, we have two cases. Okay, the first case, we can find our element, and I will mark this as predicate is find. Okay. Of course, so we here is the finding the element, but if we not finding, then we want to find the they want to find the predecessor. Yes, we want to find the predecessor of the element if we not find it. And I will call this is find predecessor. In this case, if we find our no. Yes. We searching for predecessor, but also we searching for case then we can find. If we can find the element, we solve the task. If we can't find the element, we return the predecessor. Okay, and we continue our recursion. So if I find predecessor, then I have the result actually. So I can remove the pair with the first candidate C1 and the second candidate C2. Yes, of course. I think like this, and of course I need to do definitions. Definitions here. Later I will do them, but otherwise if we not find, then we start our iteration process. We want to remove the solution from the left, and I will use go left function. And this function, what it will of course receive some namespace, these solutions, and I must do so this is the elements lower than predecessor, and I let's mark them as candidates. candidates from the left. Okay. And here I need to do the definitions. Okay, then I have defined C1 and I need to define C2. What is C2 here? We can say that C2 is equal we need to subtract from K our C1. Okay, so because we want to find C1 plus C2 equals to K. Okay, and this information tells to us how we can find C2 here, and I defined it like this. And here we go closer to our searching function or the predecessor or the element of itself. So I will name this function find predecessor, and this function will find the predecessor, find the element, its index or predecessor, and it index. So the type signature of this function will be, I think it will be like this. So we have some orderable A, we have some list in which we want to find the element. We have the element which we find, and here we have two cases. If I assume that we have predecessor and but of course there is a case then we have no predecessor. But let's simplify, let's make this function not total. At this point maybe I fix this later, but if we have we can either find the element, either define the predecessor of this element. So we can can be into these cases. Okay, and let's mark them. Of course, they can use for this the either type, and if we find the predecessor, they'll use the left constructor with the pair of our predecessor index, and I think actually I can use just index predecessor index here, and for the if I find the element I will use the right constructor to determine the case if I found the element index itself. Okay, I think like this. So here we can say that we find the element index or predecessor index, and we have second function which search to us the successor, and here of course we can find the element or successor index, and of course we need to implement these functions, but I will skip this moment at the moment because I want to use just their type signatures. So using this predecessor function I can define this thing. I can define this name. Actually this condition will hold if my find predecessor will return to me the right part. Okay, in the right constructor, then we find the element itself. So I can check if it is right, and I need to use this function here, find predecessor on our list XS. So we search it in this sublist. And what do they search actually? They of course search, we search for C2, our second candidate. And we can find it. If we find, they have the right constructor here. And this tells to us what they find. During the search of a predecessor, we find our element. But of course, they cannot find the predecessor. And in this case, they go to the left. And they need to define these candidates from the left. And how we will receive them. Okay, they have this tail XS. And they have predecessor index. They have the predecessor index. So we can use the split add function to with our index, predecessor index, to split our XS. Okay. And they take as the candidates, they take the first part, the left part of this split. So we need to take first. And this need to ask the candidates from the left. I think like this. Yes? I think yes. And last thing I need to define here is predecessor index. The predecessor index is defined like so actually defined like our find predecessor function. We take our find predecessor function, we take our XS and candidate and search for candidate 2, and they need to we will have this left here, and they need to extract it from left, I think, from left. Yes? Yes, in this case they extract it from the left. And I think we have one case here. What is the have no predecessor? Is no predecessor. Then they can actually they can stop here. They have no solutions. This means to us that they didn't find the element, and we haven't all our elements from the right is greater than our candidate 2, and this means that they have no solution because we have no at the left we have no possible candidates. We can stop here, and I want to rename this a little bit. Here we saying that we is find element with predecessor. So actually this search for element here but also want to find our predecessor if we not find the element. So with some kind of binary search, I will talk about it a little bit later, what we will use in this find predecessor function. Actually, better name here is find the lem or predecessor. I can find the correct, the nice name for this flag. Is find a lem or predecessor, and we want to catch the case that we find a lem. I don't know how. Okay, let's mark it like this. Is find a lem. This tells us that we find a lem, not predecessor. No, what I'm doing, better to just say is find a lem. So we find a lem, and in this case the is find a lem, yes. If we find a lem, we have result. If we have no predecessor, we return nothing, and otherwise if they have predecessor which say to us that we have possibly have the solutions, and we go from the left without new space of possible solutions. And also here, when we take the first part of our solution, so we have this predecessor index and this split array into two parts, and everything that is greater than predecessor we skip and we take the first part, but also we need to remove the first element in this part, because it was used here in candidate 1, and it doesn't satisfy to be the candidate. So we skip him and we do it with tail function. So we take tail of this list. And I think that's all for go right function. And using same logic, we can write the go left function. And I think it's time to define the go left function. Go left function, it takes some sublist. We can mark this sublist as XS, I think. And here we also have some cases. What if I find the lem? If I find the lem, that's what that's say to us. So at first, of course, I think I need to return just and just pair, and we have also C1 and C2, but of course I need to define them. I will do this later. If there is no successor, what if there is no successor? Then we return nothing. And otherwise, we have possibly the solutions from the right, and that means that they need to go to the right, but they need to we need to build a new list with the new solutions, possible solution space. Okay, I think something like this. And we need to do definitions. How we define candidate 1? Candidate 1 is the last element of XS. Yes, the last candidate of XS. And what is the candidate 2? The candidate 2 is candidate 2 is defined like we do in this case, so we need from K extract C1. And then we need to define this flag. Is find lem. Is the find lem. We find the lem if we have right in our function of find successor. And we do this in our XS list. And we search for C2. Okay. When we can say that we find candidate 2. Otherwise, what if we not find it? If we not find it, like in this case, we can copy it from here, but we have successor index, and we extract it from left function from our find successor function on our list with candidate 2. So we find the successor index. And using this successor index, we can find our new solution space. So here I think we can use this, but do symmetric modifications. So we using our successor index split our list into 2 parts, and then we take the second part because first part contains element which are not satisfied to our solution, but possibly we can find the solution in the right part. And we need to, what we need, tail here. So we have here find our candidate solution from the right, and we use last element as a candidate. So we need, I think, take init here. So init removes the last element, as I remember. Let's check this. Init 1, 2, 3. Yes, init removes the last element. We take init, and we have our new solution space, and we can run our go right function with our new solution space, like this, I think. So I think something like this will implement this logic. So let's do a little bit formatting. like this, I think. 1, 2, 3, 4. And also I will remove these guards to new lines. Okay. Okay, and now I think I can implement these two functions, find the predecessor or successor. So actually I find the element. If I can do this, I want to find the predecessor. And I want to provide the index in this list. What I want to do at first, I want to change these types. I rethink this thing, and I don't want to use the either type here. The left for the predecessor case and the right for the case then I find the element. I want to just use the maybe type and provide a pair of the index and the element itself if I find it. So if I find the element, I will provide its index and the element. And if I find the predecessor, if there is no element, I will find the predecessor. I will provide the predecessor here and its index. And using this, I can catch the case if I find the element itself by comparing this to second element, or I just find the predecessor. And to implement this function, I want to use two functions which I already do in some of the previous videos. The first function is binary search in the list, which provides to us the index, but I do some errors there and I want to fix them now. And the second function is a function which will just find the predecessor in the list. So not actually the element, but its predecessor, or returns me nothing. And combining these two functions, I can implement this function, which I need here. So now let's go to the binary search in our list function. It implemented here. And if I run this function, for example, on this array, you can see here they have error because I do the splitting here. And actually, I didn't catch the case. What if I can do this split? So I can do this split. I can possibly be in case then I have, for example, only one element and it go to the left, and in this way I can and pattern match the empty list like this. So this means that I need to handle two cases here. What if I have the empty list X in my binary search? Actually, there was a video about this function and you can see it. You can see link in description or below. Okay. So I can be in the case, then I can find my element. So this means that I have the empty list here. And in this case, I need to provide nothing. And also, there is a case when I can and pattern match this thing. And this case is equal to when I have some candidate, and I have a list which contain only one element A. Okay. And what I need to check here. So if my element is equal to element which I want to find, this is actually the last element in the list, then I can say that I want to return just this index, and otherwise I will return nothing. Okay, let's try to recompile this. Recompile and run. Okay, as you can see, this thing works. And I think everything must work as expected. But what if I have some duplicates? As you can see, I need to, in this case, I need to, in the case of my task which we're solving, we need to find the rightmost duplicate. So this is this 3, the index 3, and it works as I want actually. But will it work as I want it in all the cases? What I have 3 here, and you can see it doesn't catch this case because it stops at first find an element. And this means that I need to go to the right, then I find the element, I need to go to the right as much as I possible to see the duplicates of this element, and I want to provide the rightmost index. No, I am wrong. Sorry, if we're solving our task, I don't need to find the rightmost or the leftmost because I search for I just want to find the element. If I found it, I solve the task. So this function we can use this function as it is. I don't need to do any modifications. Maybe so I don't need it because if I find the element, I found the solution. I find 2 numbers. But maybe if I want found all the possible pairs of 2 elements which satisfy the condition that the sum is equals to k, then I can need this function which takes the rightmost search find element or the leftmost, because in this case I need to continue our search again, then I will until I will find all these pairs. Okay. So for maybe I will talk about this a little bit later, but let's just use this function as it is. Of course, we must understand that this is this function which just implement the logic of the binary search, and in this case, because it is use list not array, it will not will be in log search our element in log time, but the algorithm is the same. We can just change our structure, and the logic is still the same to do, and we can optimize easily this. Okay, so let's use this function in our algorithm, in our main task. So here I will need this function to do the binary search. Okay. And also I need this two function for. So at first step, I do the binary search of the second candidate. If I not found it, if I found it, I found solution. If I not found it, I want to try to find the predecessor or successor. If I found the predecessor, I can continue my searching. If I not find it, this means that I have no space to solutions and I can stop. Okay. And also I already do the videos about the finding the predecessor and finding the successor. So we have I think these two functions. I will just use them. I will just copy them because there is a video about them. You can see it if you want. Please see links in description. But now I will copy them here. So this is the functions which sorry, I need to modify them because I need index. I need index and this function doesn't provide to me an index. And this means that I need to modify them. So I think I need to fix these implementations. I need to add here the so as they do in the binary search, I want to add some count before. So how many elements they have before when they go to the right. And let's do this. They have extra parameter here, count before. And the initialize it at 0 here. Okay. And also I need here to return not just an element and also its index. Sorry. What if I not do do the I can I can find this element, this function, this function without count before, as it is, yes. But what if I found this element and then we'll search it with a binary search to find its index? Why not? So I can do this. So what I mean, let's comment this code here and load this file. So if I can use find predecessor to find predecessor in this list, for example. Okay. For example, I want to find the predecessor of 5. You can see this is a 3. And then I can use this binary search to find in the same list. I can use the binary search to find the index of 3. So, and that's how I can find this predecessor index. But I also have the problem here because this implementation of a binary find predecessor is used to list which have no duplicates. This is the problem. What if I have really duplicates like this? I think here we can have some unexpected results but I need something clean. What more clean? What happened here? But this binary search will give me the element. It will give me the element which I want to find, index of this element, but it will give me with some randomness. And I want to remove this randomness, so I want to take the rightmost element if I have duplicates, or the leftmost element if I have duplicates. So, and I need to little bit modify this code. So this means that I stop here. I need to modify one case, then I stop here. If I find my element, I return an index. But in implementation which I want to do, I don't need to stop. I need to continue to find my elements because there is some duplicates possibly in the list. I want to continue the searching, but at this point I will also remember the result and transfer it to the next iteration. So this means that I need to add some arguments here, and I need to continue my search until the end, I think. So let's do this. So extra parameters. Let's add some extra parameters which carry our solution candidate. I will call this candidate C. And this candidate will be the just value, the maybe value. And that means I need to at start with nothing because I don't know my candidate. But here I need to carry my candidate. I need to know about it. I need to know. I need to have the argument which provided, and this is the candidate parameter. This is the first parameter. I will add it here. So candidate, and this is the what is CB? This CB is the count before. Okay. So here, if I find my candidate, I need to continue searching, but I save, of course, this candidate and transfer it to the next iteration. And also I continue my searching to the right, and if I continue to the right, I need to count the new this new number of elements from the left. Okay. Here, if my element is greater, then I stay my candidate as it is. And here, if my element is less, I also state as it is. And I think we need to we need, of course, to fix one in this case. How we fix it? If we find this, if our element is equal, then we return its index. But Otherwise, they return the previous candidate. Okay. I think that's all the fixes. Let's try to run this. So what if I have to find free? It's okay, but what if I have some many frees here and I expect the rightmost? And the rightmost, it tells me that it has index 6. Let's check this. 0, 1, 2, 3, 4, 5, 6. Yes, it seems it works. Yes. But what if I want the leftmost of these frees? What if I want this free? So, how do I need to change this logic? Actually, I need from here, from this point. No, I need to think. So actually I need to change one this case. Yes, as I said, we need to go to the left part of the list, because if they find something, if they find the element, we're not interested about every duplicate from the right. We only interested in duplicate from the left, and that say to us that they need to go to the left part of this list. So I don't need this to change this count before as it is, and I need to go to the x left from here. But also I must say this parameter. I'll say this solution possible candidate. But how it's better to implement this? Is it better to provide some argument here which tell to me which the rightmost or leftmost I want, or it is better to do the one more function for this case? I need to think about this. And I think it is easy to do with the additional argument here, which will give me information what I want to do. So let's do some data type here, which will provide this information. And how can I data type? I will name it, I don't know how to, I will name it LR. And this type just will show me either I want the leftmost element or I want the rightmost element in this ordering of duplicates. Sorry, in this subsequence of duplicates. And of course I need to derive equality for this type, and I need to provide this type here as additional argument. And I want to add some extra case here. No, here. This I need to add some extra guard, as I said. And this guard is so with our solution, then we want to is then our left for sorry. So we need to name this argument somehow. I will name it LR, okay. So if our LR is equal to rightmost, then we continue our searching from the right. And if our element is equal to leftmost, if our argument, when we go to the left, and then we go to the left, we stay our count before as it is, and we provide left elements. Okay, so let's check this. I think this should work. Okay, so I need to add some number of arguments. Of course, I need to provide sorry. So I think in this case they need to provide this argument, recompile, we done. And now the interesting thing, let's look at, let's run it the leftmost argument. As you can see, I get 2 because I found 3 with binary search, but I found the leftmost 3. And also I can find with the rightmost search, this is 7, 0, 1, 2, 3, 4, 5, 6, 7. You can see this is the rightmost 3. Okay, and I think this code is correct. We can use it in our main algorithm. Okay, and now I think we can return to our function implementation. Let's uncomment this. Uncomment. Also, I think I can remove this. I will just take the comments from here, find the element predecessor, and here I will use find the element successor. So let's remove, but also I can, no, I can remove. Okay, and we need to look at our main algorithm. So here we need to fix some things. So we need to fix this flag. Either we find an LM. How we determine that they find the element that this function. So actually, I need to check it for just. Okay. So this function, we run this function. B function, we have this list, this candidate, and this search for rightmost element. Okay, and we find element that this function is just. Okay, and also here we also check if it is just, but they use binary search and the search for leftmost, I think. Yes, the leftmost. Next thing we need to fix is to use this find predecessor and this find successor. We need to use actually, if we not find LM, we need to use these new functions for finding the predecessor and successor, and I will put it here. And and successor here. And of course, we can see that they had maybe type here, not either. They use from just here, from just. But also I need to catch the case if there is no predecessor. If there is no predecessor, how I will determine this thing, this case? Okay, this thing is determined with so we run with this expression, but we need to check that this is nothing. Okay. And also here, if there is no successor, we also check it like this. Sorry. Like this. But we check for nothing. It's nothing. Okay. Okay. Now let's try to compile this. Of course, they need to fix some errors. Okay, and the problem is that I use find predecessor here, and it returns to me maybe. Okay, I try to extract just, but here I need to provide integer, so I need to provide index by here extracting the element itself. So as I said earlier, I need to determine the predecessor index, and I want to add, and I will use binary search function for this. This means that in that case I must run my binary search function for this element, and I need to search for rightmost element. When I go from the right, yes, I need to search for rightmost predecessor. Okay. And also I think the same symmetric case we have here when I run this with my binary search, but I want to find the leftmost. And now let's try to compile. Of course, errors. Let's look at them. Of course. Here I have binary search, and what is the type of this binary search? The type of this binary search is maybe int, and it means that I need to extract it from just. To get my actual int index, and also here. Yes, let's try to recompile. Okay, next error. B is applied to few arguments. Of course, I forgot one argument. Here is my C2. And here I also need C2. It doesn't want to eat this. Okay, what I'm doing wrong. Binary search. Binary search. It takes the first argument. It takes our list that you want to find. Okay. So we need to provide the list here. Access. And as a second argument, we need to provide our predecessor. Okay. So here we're searching for predecessor index. At first we find this predecessor for our candidate, then we extract the element itself and use that element to find it in a list with the binary search. And you want to use the rightmost element. And the same thing we need to fix in this case, I think. So like this. Please compile. No. Okay, something other. Ord A. C1 ord A. Okay, I think we need to. So we want to have the numbers also here. Numerics. Okay. Because I do subtraction when I find the second candidate here, they must add this constraint here. Yes. And we can try to run our function. What if I have some list, sorted list, and I want to find I don't know, maybe 7. 1 and 6. Yes, it works. Let's try something. What if they have duplicates, for example? And what if I want to find 4? Yes, it works. But what if I have like this? Yes. So as you see, this works, and it must work pretty fast in the logic. But of course, this binary search on the list, and it's only a logarithmic time in theory, because this is a list. We must move through arrays, but logic still the same. Okay. So this is the whole implementation. Let's look. And this. Okay, let's try some more examples to check, to verify that our program works. So for example, if I have 1, 2, 2, and what if I want to 5, 11? Okay, you can see this is pair 6 and 5. What if I have 2 numbers and I want to find 3? This is 1 and 2, and if I want to find 5, they have exception. Okay. Tail empty list. So I think I need to check some corner cases here. Okay, now let's add these cases. Then they have empty list. In this case, they need to return nothing. Okay, go left, the empty list. Let's reload and run. Empty list. Why this happens? It's look, I don't see something. So I think the problem is that here then I try to take the init or tail. I can be in case then I have the empty list, and that's why program fails in that moment. So to fix this, I need to do some additional checks. So let's do some additional naming here. So I will name it as like this with underscore some intermediate result, and now I think I can do some checks. So I think here I can check that if empty my CCL candidate solutions from the left, then I need to have the empty list. Otherwise, I can take the tail of my CCL. Okay. And also the same thing can be done in the next symmetric case here. So I can extract these like I think like this. I can use here, take init. So I think something like this. Empty. So I think I need to import data list module to check the empty. Empty. There is a empty. This is strange. Because I need to use null function to check the list is empty. Null function. Okay, let's look at this. Null, any foldable can be checked for empty. Okay. And run our function. They have nothing. And the 3, they have something as a pair. Okay. 4. Yes, it works. It doesn't work. It doesn't catch this case. Why? Oh, why this happened? Let's try to add some numbers here. And in this case, it find but in this case it doesn't find. Why it doesn't find? So I do a little bit debugging and I realize something that I doesn't I expect this. I doesn't need this tail here, because if I do the split of the list at some point, the median is go to the right part. So I didn't do any split here. Oh, sorry. I didn't need to take tail. Why I take tail here? This is very strange. Why I decide to take tail? Here I take init, but here I decide to take tail. I understand why I decide to take tail, because here I already do a pattern matching and I remove this first element, and as a candidate 1, here I try to remove candidate 1, but I didn't need to do this because I already do this here. So this means that I can define my solution from the left as like this. Okay. And I don't need to do any more things. But here, actually, I need to do the remove because I don't do any pattern matching here. Yes, and I need to, as I take the second thing from my split, I need to take the remove the do I need to remove? Yes, I think I need to remove the first element. No, I think they didn't need it here also. Because they find the solutions candidate here from the right, okay? After the successor, and the successor itself must be in our solution space, because this is the first candidate, and actually when I split, it goes to the second element of the pair as the first element. So I can define it, I think, like just this, and I don't need this code. Okay. Let's reload and try to run our keys. Then it don't find. It don't find again. Fuck. Something broken in my logic. So I think I found another problem. What it is here. My predecessor index, it goes to second element, so the second element itself must go to the my space solution. So this means that I need to take my first element and add to the end of it the predecessor, because it's in the second part at the first. What is the better way to do this? And I think it's better way to do this is just to increase this index. I hope this not doing any side effects. Oh. Yes, so I take +1, the next other after my predecessor. And this will remove my predecessor to the first part of the to the first pair of splitting. For example, if I split here at position 1, the element with index 1 goes to the second part. But if I do the split at 2, this will move this predecessor free to the second part. Okay. And now let's try to run again our case. I reload. I don't reload. Yes, it works. Yes, it works. 9, 11. Okay. I hope that it will work for any case, that I don't do any errors. If you see these errors, please write comment. But what if I want to find all the pairs, all the elements which give me my sum? So let's implement this case also. I will copy this function, copy paste it here and name it f underscore. And here I need to change my maybe to a list of pairs. Okay, I don't need to use nothing here because I can return the empty list if there is no elements. Okay. And here, of course, I need to have some extra parameter in my helper function which will collect to me the all possible pairs. I will call this argument f, find element pairs. Oh, we can call it fp, find pairs. Of course, as an initial, I can provide the empty list because I don't find any pairs. But here, I need to. So if I have empty list, I need to return empty pairs. But what here if I have some solution here? So here the replace our nothing with our find pairs. But if I find element, I don't stop. I just add this found pair to my. So I continue to left, and also I add my found pair to my found list. I think like this. And here, if I not find an element, I just stay my found pairs as it is. Yes, I think like this. I hope my find predecessor function will catch this case here. So let's check it. Is my find predecessor will find me the predecessor of the element if it is in my list. Yes, it find me. This is 2. Okay. Yes. So I can use it to find my solutions here. Okay, and same thing we need to do here. We also have our find pairs, and here we return our find pairs. Here we go to the right with our find pairs, and here we also go to the right. So here we return our find pairs, and here we go to the right with our modified find pairs. We add this here. Okay, I think like this. And let's check. F underscore some array. And for example, what if I want to find 6? I get an exception. Data maybe from just. Okay. From just. Here I'm using from just. So this happens, I think, because we actually have no predecessor here, but I try to go. If I know predecessor, I have no solutions, but I try to use it, and this means that I need to check the extra case if I have no predecessor here. So I can find the element, but this element can, in this case, we can have that, we can be in the case that there is no predecessor. And that's lead us to a problem. So I need to check it here. So I just need to add some extra case. I think this will be more readable if I just add one guard here, and here I will. So if there is no predecessor, then I need just I can't continue my search anymore, and I need to stop here this list as a result. But otherwise, if I find the LM and I have the predecessor, then I can continue. Okay, then I can continue. And also I think I need the same logic here. So if I found the LM and there is no predecessor, I need to return my result as it is, and otherwise I will continue my search. Variable not in scope. Of course, here I use this flag to determine have a successor or not. and the done. Okay, compilation is done. Yes, I find all the pairs. I hope this is all the pairs which give me the sum. Okay. Let's add some pairs, some elements. For example, I can add 6 and 0 here. And in this case, I have the 6 and 0. And if I add the 7 and minus 1, it will give me the 7 and minus 1. Okay. So let's do some commenting here. Find all pairs A and B such that A plus B equal to K. And here defined only one pair A and B such that A plus B equal K. Here define the successor, here the predecessor, and here define the element index in a sorted list, the binary search. Also, we will find the leftmost or rightmost. Okay, using this data type. So guys, I think that's all for today. We write this program which allows to us find two numbers in the given sorted list which in a soon give us a certain number. And I think this algorithm is pretty fast, but of course it will not work as fast as in the theory, because I'm using the list here. And but the logic is but this logic can be easily transferred to an array, and this algorithm will work much faster. So in the next videos, I think I can try to expand this problem and find the subset sum and solve the subset sum problem in this way. Okay.